Hello everyone and welcome to today's video. In today's video, we are going to try to understand Lamport clock. How is it used and why are they used, and how exactly they can solve the problem of ordering of events. It is in general important in software systems, but let's say you have a distributed key value store or a cache, and you want to understand what was the latest value added into that cache. Then distributed systems, how exactly do you implement mutual exclusion to ensure only single process can enter the critical section? How do you debug in a distributed system? How, if multiple services are involved, how to identify when exactly an event occurred, which event occurred before the other one? And collaborative editing, Google Docs or shared notes, where depending upon who wrote the final value has to be synced across multiple servers and multiple copies. So these are just few of the cases where order is very important. In a single threaded system, this problem is more or less in control, because you will have a single physical clock and you can attach the timestamp of that clock for each and every event. And just by identifying which events the timestamp is lesser than the other one, you can identify the order. So problem is more or less in control.
Is single threaded system different from a single process system, or is it same?
Single threaded system or single process system is more or less same, but a single process may have multiple threads.
Okay.
Got it. In a distributed system, however, there are multiple problems. First is, since multiple nodes may be involved, multiple servers may be involved, then there's no single physical clock that can be used for the timestamps. Why? Because physical clocks can go out of sync. And on top of that, most of the clocks have precision of only a few milliseconds. And since multiple clocks are involved, all of their precision and error will be different. So identifying the exact order or identifying the order can be very error prone. And thirdly, synchronization across multiple servers can be very resource intensive. So what is the solution? So Lamport clock is one of the solutions which can help you establish partial ordering in a distributed system. It is what do we mean by digital clock is, instead of using the timestamp from a physical clock, we are going to use counters. And these counters are updated in a specific way using a very well-defined algorithm. And this helps us establish the partial ordering. Partial ordering means we will not be able to establish the exact ordering for all the events in the entire system, but we will be able to identify the order of some of the related processes, some of the related events. If A and B are two different events which are happening in the same process, right, and the process is single threaded, then and A happens before B, then we say A happened before B. This symbol means it has happened before. Let's say there is a process P1 which sends a message M to process P2. The sending of the message is called event A, and the receiving of the message by P2 is called event B. Then we know sending has happened before receiving, so that means A has happened before B. Third is, if A has happened before B and B has happened before C, then we can imply that A has happened before C. And finally, if A has not happened before B, there's no relationship, we are not able to identify this relationship, and B also hasn't happened before A, then we say A and B are concurrent. So the Lamport algorithm is very simple. What it says is that every process will initialize a clock of their own to 0 to begin with. let's say there are 3 processes, P1, P2, and P3, and all of them have their clocks initialized to 0. Anytime a local event happens on any of those processes, then we increment the value by 1. While sending the message from one process to the other, the sending process will increment its clock value and then send along with the message. And the process which is receiving the message, it will check the timestamp it has received, compare it with the current timestamp it has, choose the maximum, and then increment it. If a message has been received by a process Pj from Pi, and that message must have been sent before it has been received, that implies that the clock value of the event which has happened before has to be lower than the clock value of the process which is receiving it. So in this case, we see that if timestamp which has been received is higher, then we need to update the clock value to more than that to be in sync. If, however, the current clock of the process Pj is higher than the value which has been sent, then we don't need to update it. We can simply increment it. Let's take an example of a distributed key value store. Over there, we have 2 servers and 1 client. All of the clocks are initialized to 0 to begin with. Client's clock is also initialized to 0. Server clocks are also initialized to 0. Write request comes, client updates its clock value to 1. Then it is sending this value to be returned to server 1. It sends key is equal to value and clock is equal to 1. The server has received the message. It checks the clock value, sees that the clock value of the message that has been sent is 1, whereas its own clock value is 0. So it picks 1 and increments it by 1, sets the final clock value as 2, stores the value in the system with key is equal to value and t is equal to 2, and responds back to the client saying, I have written it at clock is equal to 2. Now the key needs to be changed to 2. In this case, the client is sending the request to server 2, and the server 2 receives this request that key is equal to 2 and clock is equal to 3 from the client. Server 2 checks its clock value, compares it. It sees that its own clock value is 0, but the clock from the client is 3. So it updates its clock value to 4 and sets the data in its system as key is equal to 2 and t is equal to 4.
So is client updating the clock value on its own side?
Client, in this case, client is updating the clock value on its own side as well.
Okay, so the client is going to update it to by 1 before sending it to server, and the server is going to update it again.
Yes. So client is following the Lamport clock algorithm only. It also has implemented it in the same way. So it will have 2 values, key is equal to value at t is equal to 2 and key is equal to 2 at t equal to 4, and it can compare both of these and find which one is the latest.
So what is client here? Like, is it the application which let's say with respect to database, which talks to database, or it's a web interface for the server 1, server 2? So
it can be an SDK, it can be a web app in the middle. Any system which is interactive.
My question is basically, if client is application, then isn't it like a overhead on to the client side of maintaining these Lamport clock? Shouldn't this be like only on the server side?
Yeah, see, this is one of the implementation in which you can let the client decide the order or the latest value, and client can resolve it on its own. The other solution is, of course, that the servers they sync the data amongst themselves and update to the latest value. Let's say how now replication and syncing of the data will happen. So generally, in a distributed system where replication is involved, you will have a process which initiates synchronization of the data. Server 1 is going to initiate sync call. It says that I have key is equal to value and t is equal to 2. My clock value is 3. Server 2 receives it. It compares the values. It sees that, okay, for this particular key, my value is 2. And since my timestamp is higher than yours, I'm going to send that to you. So there are 2 things happening over here. First, server 2 received this event of sync. So it incremented its clock by 1. And then after processing, it is sending the response to server 1 as well. So that is another event. So clock value of server 2 goes to 6. It tells server 1 that my key is 2 and t is equal to 4. Update it to this. Server 1 accepts the request and changes the value in its system.
But in the response, why t is equals to 4 and not 6?
Okay, good question. This t is not the clock of the server or the processes. This t is the timestamp or the version of this value. This is how client or any other process is going to identify which of these values is the latest value. So this is called version value. So where you store the exact value of the object, and in addition to that, you store the timestamp as well. Actual clock on the system is 6, but this particular value was updated when clock was 4.
So basically, it's the timestamp of when that event happened.
When this
The Lamport time.
updated at event for this. So this is it. This is how Lamport clock actually works.
Okay, so one of the examples would be multiple masters, syncing between multiple masters.
Correct.
only thing I'm confused about is कि client side से जब data आता है तब भी clock update होती है या only when replica synchronization happens?
The clock is updated at every event.
I have a quick question on that, Baljit. So when you say the clock is updated on every event, is the clock going to be different for all the clients, or is it going to be same for all the clients? So now let's say over here there is only one client, but let's just say we have 2 clients. In that case, what would happen?
All the clients will have different clocks because all the clients can be thought of as different processes.
Why do we call it partial ordering and not like full ordering or something?
Let's take this example. So in the original example, we had client 1, which was interacting with server 1 and server 2. Let's assume there's another client which is talking to server 3 and server 4 in the same system. On the client 1, the key is equal to value and key is equal to 2 are updated, and their timestamps are t is equal to 2 and t is equal to 4. So over there, I know that key is equal to value came at 2 and key is equal to 2 came at 4. So the latest value is key is equal to 2. Let's assume similar process happened on client 2, where initially foo is equal to bar request came via server 3, foo is equal to 2 request came via server 4. In that case, foo is equal to bar timestamp will be 2 and foo is equal to 2 timestamp will be 4. Although I know that foo is equal to 2 is latest, but I cannot tell which of these came first, whether key is equal to 2 was set earlier or foo is equal to 2 was set earlier.
These are quite unrelated events, right? Like, so in this case, we are not able to figure out the ordering. So let's say if it was like server 1, server 2, and server 2, server 3.
Server 2, server 3.
Yeah, in the second client, if it was server 2 and server 3,
and it was server 3.
Was there a chance that we could figure out the ordering in this case because we have one server in common?
Yes, in this case, the ordering will be possible, but it will be only one of the orders because we know that server 2's clock value was 6 at the end of the last operation for keys equal to 2. So instead of keys timestamp is equal to 2, the value here would be probably 6 or 7, and we will be able to order them. Now, since a common node or common server has been involved, the ordering becomes possible.
Is it always true, or like only if server 2 was handling the request? Like, let's say if for the first case, server 1 handled the request but synced it to server 2, and in the second case, server 3 handled the request but synced the replicated data to server 2.
In that, so the moment the processes become connected, the moment they start interacting with each other, then the ordering becomes possible.
No, I just want to understand whether it will go into relation like A happened before B, or it will go in the relation of it can also go to the concurrent behavior wala part, because both of these events can also be concurrent, right?
In this case, these are concurrent events only. We cannot apply any happened before relationship over here. So partially order will be possible only where a common process was involved. So we learned about Lamport clocks, how they can help solving about ordering or finding the latest value in a key value store. Let's learn a little bit about the limitations. First is that it helps us only do partial ordering. Like in the example we discussed a few minutes back, if server 2 was not involved in the writing of or foo is equal to bar, then we cannot identify the order in which both of those had happened. Writing of key is equal to value versus writing of foo is equal to bar. Second is it tells only one of the possible orders. Third is concurrent processes are not handled. So we cannot identify which of the concurrent events happened earlier than the other. And finally, one of the key challenges over here is if A has happened before B, then we can be sure that clock of A will be lesser than the clock of B, but the reverse is not true. So that is, if you see the clock values of two events as higher or lower than the other, it may not mean that A has happened before B. It may also be possible that these processes or these events are completely concurrent and have no relation to each other. Right? So that's all about Lamport clocks. So today we talked about what Lamport clocks are, how they solve in certain situations, what are their limitations. In the upcoming videos, we will talk about different kind of digital clocks as well, like vector clocks, maybe generation clocks, in what kind of use cases and scenarios they can be used. So that's all from our side today. Please stay tuned for more such videos. Like, share, subscribe.